tests for uniform convergence of sequence of functions. We are going to study two tests. One is Cauchy criterion type test, and that is indeed a Cauchy criterion for series of functions for the uniform convergence of that series, and another is a test known as Weierstrass Mn-test. And Weierstrass Mn-test is very useful test that we will see. First, we have this theorem one. This test. This is a Cauchy criterion for the uniform convergence of sequence of series of functions. So, what it states, see, it has the series summation fn of functions on a domain D subset of R is uniformly convergent if and only if for each positive number epsilon there exists a number, a natural number indeed this, which depends only on epsilon, such that for all m greater than n and n greater than or equal to m epsilon, the sum, the sum of the terms of the series starting from fn plus 1 x plus fn plus 2x plus 1 plus fm plus fm at x mod of this term is less than epsilon for all x belongs to T. So this is the requirement for a series of functions to be uniformly convergent. That means this piece of sum you have what it says. It says that suppose you have this. This is a series. Let us just suppose this is a series. This is made up of some terms f1, f2, f3, so on so on. Suppose here you have fn plus 1, so on. You have these things. What it says that after certain stage, for each epsilon there must be a stage. That stage is this m epsilon, and let it be somewhere. This must be capital M here, so that after this epsilon, whatever piece of sum we take, whether we take it small or whether we take it large, or whatever piece of sum we take, that piece of sum, absolute value of that piece of sum must be less than epsilon. This is the condition. And it is not that कि आप छोटा सा piece ले लेंगे sum का. You may take m as large as you wish to be taken. You may take n to be as large as possible, or m to be as large as possible, or you might even if you take n to be just the place from where this stage starts, m epsilon, and you may take m to be as large as possible. Still the sum, whatever sum, because what I am saying that is you take m to be as large as possible, because if you fix this n and you take m large, then the number of terms in this sum will become more and more, and but still the overall modulus will remain less than epsilon. So this is the idea of this Cauchy criterion. And now we have to look at the proof of this beautiful result. And let us take Sn. This is I'm denoting by Sn the partial sum first n terms of this series, or you can call it the nth partial sum of this series, summation Fn. And now suppose first that series summation Fn is converging uniformly to some function f. Obviously it converges uniformly, then it has to converge to some function f. And what it means when we say that the sequence series converges, that means its sequence of partial sums converges uniformly to that function f. So that means this sequence Sn of partial sums converges uniformly to f. This is the definition of uniform convergence of series. So what it means then, let's use the definition of uniform convergence of sequence now. That says that whenever we choose some epsilon positive, there will be always some number uh, positive number, positive natural number, which depends only on epsilon, that is m epsilon, such that the convergence definition is this thing, that this Sn x minus f of x mod of this difference has to be less than, I can choose it to be epsilon by 2. I'm just taking epsilon by 2, and this will hold for every n bigger than or equal to m epsilon, and for each point x in D. Why it happens is for each point, because the convergence is uniform. Okay, now we have to use this inequality. Keep in mind this inequality is 0.1, and we have to reuse it somewhere. So now let us choose m to be greater than. We can take m to be strictly greater than. Indeed, that would be much better. Let's take m and n, but both needs to be larger than this capital M, so that we can use this 0.1 wherever we have to use, and the x be arbitrary point in domain D. Then from equation 0.1, but 0.1 will be used at the last two steps. But first, we have to show this number to be less than epsilon. But let's see what this number is actually. You see, Sm is, I'm not using x, Sm is sum of first m terms, f1, f2, and you are taking m to be larger than n, so you have to pass through n also. It has to be n plus 1, so on, it will be up to fm. And what is Sm? You know, you can see from here why to write separately Sm. You see now, since m is larger than n, तो first n terms का जो sum होगा वो यहाँ भी appear होगा, तो you can write it as Sn plus fn plus 1 plus fn plus 2 plus so on plus fm. And what you can do now, you can shift this Sm Sn to the left hand side, so you get the value of this difference. And you see the value of this difference is nothing but this is fn plus 1, fn plus 2 plus so on. So this is the difference. Okay, so you have this thing, fn plus 1 x is equal to smx minus snx. And now what I'm going to next step, I have to add in this number, I am just adding fx, and I'm subtracting fx at the same time, so that this inequality can be written as smx minus f of x plus f of x minus snx. And now you use the triangle inequality. Triangle inequality will give you that this is less than or equal to smx minus f at x, plus you can write fx minus sn of x. But that's true, that's not a problem. Smx minus f at x प्लस मॉड ऑफ, क्योंकि मॉड के अंदर आप एडजस्ट कर सकते हैं चीजें, मॉड ऑफ एज, बिकॉज वी नो दैट mod of a is same as mod of minus a, so I can write this fx minus sn of x as sn of x minus f of x. So with this, I have this next inequality there, that as this mod of sm of x minus sn of x is less than or equal to this number, mod of smx minus f of x plus sn of x minus f of x. At the beginning, I had chosen m and n to be greater than or equal to m epsilon, and from 0.1, we know that whenever these numbers are greater than or equal to m plus epsilon, then this smx minus f of x is also less than epsilon by 2, and the other number sn of x minus f of x is also less than epsilon by 2, and taking the sum of these two is epsilon. So what we get that this sum is less than epsilon whenever m and n are greater than or equal to m epsilon. So this was the requirement for the direct part, when we assume that the sequence series is a uniformly convergent. Now next we have to assume that this type of inequality holds, that these sums are smaller, arbitrarily small, and then we have to show that this series is uniformly convergent. So for the converse part, suppose for each epsilon greater than 0, there exists some number m epsilon depending upon epsilon, such that whenever we choose m greater than n greater than or equal to m epsilon, then we are given this inequality. Let us give this, I have named it as 0.2. We have some observations as noted previously, that this whenever m is greater than or equal to n, then Sm of x minus Sn of x is nothing but is the sum Fn plus 1x plus so on up to Fm x. And so what it means, it means that it is given to us in 0.2 that this sum is less than epsilon. So that means Sm of x minus Sn of x is less than epsilon for all n m greater than n greater than or equal to m epsilon, and this is also true for each x in t. That means this is a Cauchy sequence, and since it this m epsilon m is depending only on epsilon, so we call it as a uniformly Cauchy sequence. This is a uniformly Cauchy sequence. This is a uniformly Cauchy sequence of functions on domain D. Okay. So now let us, since this inequality holds for every epsilon, what we are going to do, we are going to fix some epsilon. Let us take epsilon to be 1. And then accordingly, we will have a number which will depend upon epsilon. But since we have a epsilon equals to 1, so I denote this number to be m of f1. So and let us choose n to be a number which is greater than m. Strictly, I'm choosing it to be strictly greater than m. Then from equation, let me see. I can then for because this equation 0.2 holds for every epsilon, so this can be applied for the choice epsilon equals to 1 also. So let us see. This holds for whenever you have two numbers, one written as m and another written as n, and both these needs to be greater than this m epsilon. So what I'm going to choose, I'm going to choose one number n, and another number I'm going to choose as n minus 1. See why? Because n is greater than m epsilon, so n minus 1 cannot be less than. So it has to be greater than or equal to m epsilon. So both the numbers n and n minus 1 satisfy the condition required for inequality 0.2. And but this has to be less than epsilon. But you see this difference. Sn is the sum of first n terms, and Sn minus 1 is the sum of first n minus 1 terms. So what is left to you is Fn. So this means that Fn of x is less than epsilon, and epsilon we have chosen to be 1. And this is true for every x. So this is the inequality here now, that mod of Fn of x is less than 1 for each x in T. So what it proves, this inequality proves that for n greater than or equal to m1, that means n greater than or equal to m1 are those numbers, that is m plus 1 is a number which satisfies this inequality, m plus 2 is a number, so m plus any number 3, so on up to m plus p, where p can be any number greater than or equal to 1. All these numbers satisfy this inequality that I have boxed here. So this inequality also says that whatever function this is, Fn of x is a bounded function. It means, because what is the definition of a bounded function? Bounded function means that f of x has to be less than or equal to some constant k for each x in the domain of the function. So here you see that this inequality in the box holds for every x in domain D. So this means that each such function Fn x is a bounded function, means wherever n is greater than or equal greater than m plus 1, this function is a bounded function. So I have written it here that this shows that each function f m plus p, obviously m plus p means I'm taking n to be this number, because you don't need to be bothered about it, because this needs to be greater than m, and truly this is greater than m. Fm plus p, where p can be 1, 2, 3. Every function is a bounded function. So what we know, what we know now, this is a bounded function. Okay, let me see. In inequality, we are given something in this equation 0.2. Now let us form the partial sums. Let's form the series. क्योंकि हमारे पास सीरीज क्या थी, हमारे पास सीरीज है एफ एन, जिसको आप लिख सकते हैं F1 प्लस F2 प्लस F3 प्लस सो ऑन प्लस, हमारे पास एक स्टेज आई है जिसको मैं FM रख रहा हूँ। उसके बाद की जो टर्म्स हैं उन टर्म्स को मैं लिख सकता हूँ P इक्वल्स टू 1 टू infinity. This is FM plus P. So this is a series. So what I'm going to do, I'm going to just for the time being ignore these terms. I'm going to ignore this first M terms, and I'm going to focus on this part of the series. I'm going to focus on this part of the series. So let us take this to be the series now of the focus, जिसमें हम focus करेंगे और इसके partial sums form करेंगे. तो let me denote its partial sum TP with P, and let it be what it has to be. It has to be F of M plus 1, first P terms का sum, F of M plus 2 plus so on plus F of M plus P. And this inequality, यहाँ पर ये जो inequality है 0.2, इस inequality से you get to see that this is a sequence. TP is a sequence, and this can be seen from here that this sequence of partial sums of this new series, जो new series नहीं है, we are just deleting for first few terms of the original series, and whatever is remaining with us, we are studying that. So we see that then this is a Cauchy sequence. This is a uniformly Cauchy sequence of bounded functions now. वो इसलिए कर रहे हैं क्योंकि अभी हमने पहले ये प्रूव किया कि ये सारे के सारे फंक्शंस, अब ये जो न्यू सीरीज में बना रहा हूँ फ्रॉम p इक्वल्स टू 1 टू इन्फिनिटी FM प्लस p, ये बाउंडेड है, ये सारे के सारे फंक्शंस बाउंडेड है, और ये बाउंडेड फंक्शंस की सीरीज जो बन रही है, दिस इज अ कॉशी सीक्वेंस, दिस इज इसके पार्शियल सम्स की जो सीक्वेंस बन रही है, दैट इज अ कॉशी सीक्वेंस, एंड और फंक्शंस कौन से बाउंडेड फंक्शंस है. एंड व्हाई वी आर टेकिंग, बिकॉज वी हैव अ रिजल्ट, the Cauchy criterion and for the uniform convergence of sequences, or that was stated for precisely for bounded functions. So इसीलिए I had to take this. So that means that this sequence which I have denoted जिसकी terms को मैंने T sub P से denote किया है, a partial sums of this series, this P from 1 to infinity FM plus P is uniformly Cauchy and also bounded. ठीक है, क्योंकि हर एक FM प्लस 1 बाउंडेड है, तो सम ऑफ बाउंडेड फंक्शंस बाउंडेड होता है, तो ईच TP इज आल्सो बाउंडेड. तो सो फ्रॉम द Cauchy criterion on uniform convergence we see that this sequence of partial sums T sub P is uniformly convergent. और ये यूनिफॉर्मली कन्वर्जेंट होने का मतलब है कि आपकी जो सीरीज है P फ्रॉम 1 टू इंफिनिटी FM प्लस P इज यूनिफॉर्मली कन्वर्जेंट ऑन T. व्हाट इट मींस, दैट मींस आपके पास ये सीरीज जो मैंने बॉक्स इसमें सर्कल में रखी है, ये सीरीज आपके पास यूनिफॉर्मली कन्वर्जेंट है. तो यूनिफॉर्मली कन्वर्जेंट में अगर आप फाइनाइटली मेनी अदर टर्म्स ऐड करोगे तो उसकी कन्वर्जेंस चेंज नहीं होगी. तो वी नो दैट दिस इज यूनिफॉर्मली कन्वर्जेंट एंड वी आर एडिंग अप बैक दिस F1 F2 so on up to FM. ये टर्म्स वापस इसमें ऐड कर दो, यू गेट द ओरिजिनल सीरीज summation FN, and hence this summation FN is also uniformly convergent because फाइनाइट नंबर ऑफ टर्म्स को ऐड करने से आपकी कन्वर्जेंस चेंज नहीं होगी. एंड दिस इज द रीजन वी गेट टू सी that this original series summation n from 1 to infinity Fn is uniformly convergent. Now if you have any questions, any doubts, and this proves the converse part also. Regarding the proof, if you have any question.
सर ये SN और SN माइनस 1 वाला एक बार फिर से रिपीट करना.
हाँ, ये वाला.
यस सर.
हाँ, ओके. क्योंकि आपके पास इनइक्वालिटी क्या है, लुक एट द इनइक्वालिटी.
M is greater than N is greater than M of epsilon.
आपके पास है कि जब भी दो नंबर्स हैं, चाहे हम M से डिनोट करें या किसी भी नंबर से, तो वो नंबर्स दिस कैपिटल M से बड़े होने चाहिए. तो वहां कैपिटल M M1, ठीक है, तो अगर मैं ये नंबर चूज करूं, इफ आई टेक, इफ अगर n स्ट्रिक्टली ग्रेटर देन m1 है, तो n-1 क्या हो सकता है एट मोस्ट, क्योंकि ये तो सिंपल, इसका एक एक पीछे जाना है ना, इट्स प्रीडिसेसर है, तो इट हैज टू बी ग्रेटर देन और इक्वल टू m1 ना, इज इट ओके? बोलो। You are choosing n to be strictly greater than m1, so n-1 will be greater than or equal to m, so that आपके पास ये दोनों नंबर्स, एक n है एक n-1 है, ये दोनों नंबर ये इनइक्वालिटी सेटिस्फाई कर रहे हैं,
सर
m
रिपीट
greater
करना,
than
आपकी
n।
आवाज कट गई थी बीच में।
अच्छा, we are taking n to be strictly greater than m1,
यस
okay?
सर, यस सर,
तो जब n strictly greater than m1 है, तो n-1 हैज टू बी ग्रेटर देन और इक्वल टू ना, ये एक ही स्टेप
यस
पीछे
सर,
जा सकता है ना, तो ये स्ट्रिक्ट
यस सर,
इसीलिए लिए ताकि n-1 भी ग्रेटर देन m1 रहे। अब ये दोनों नंबर्स n और n-1 जो हैं, दे आर सेटिस्फाइंग दिस इनइक्वालिटी व्हिच आई हैव केप्ट इन बॉक्स, ब्लैक बॉक्स, है ना?
यस सर।
इज इट ओके? तो अब जब ये सेटिस्फाई कर रहे हैं, तो मैं इन दोनों नंबर्स पे इनइक्वालिटी 0.2 को अप्लाई कर सकता हूँ, कर सकता
ये
हूँ।
सब हमने m को n से रिप्लेस किया, आई मीन ये ग्रेटर देन इक्वल्स टू
हाँ,
होगा ना उसके।
हाँ, यू में टेक के m को अपने n से रिप्लेस किया और n को अपने n-1 से रिप्लेस किया, यू में टेक दिस,
ये सब मतलब फिर
ठीक है,
ये इनइक्वालिटी m ग्रेटर देन इक्वल्स टू n होना चाहिए तब।
है ना?
अगर खाली ग्रेटर,
नहीं, वो कोई इशू नहीं होता उसमें, हमें एन नाम से, ये सिंबल सिंबल पे नहीं फोकस करो ना, कि आप एम रख रहे हो या एन रख रहे हो। हमारे पास ये है कि आप सिर्फ ये देखो कि जब भी दो नंबर्स होंगे, दो नेचुरल नंबर्स होंगे, वो दोनों के दोनों नेचुरल नंबर्स किससे बड़े होने चाहिए? कैपिटल एम से बड़े होने चाहिए, दैट्स द फोकस। उसको आप एम से लिखते हो, पी से लिखते हो, वो तो नोटेशन है, अब नोटेशन तो कुछ भी देनी पड़ेगी ना। तो
यस सर,
the sense is के both the numbers need to be greater than this given number capital M। तो यहाँ पर ये दोनों के दोनों नंबर्स, चाहे वो n और n-1 जैसे भी हैं, ये दोनों के दोनों नंबर कैपिटल M से बड़े आ रहे हैं ना।
यस सर,
तो जब भी ये दो नंबर इससे बड़े हैं, तो आई कैन अप्लाई 0.2, ठीक है?
ओके सर, ओके
या
सर।
दैट्स इट। एनी अदर क्वेश्चन?
नो सर।
So okay, now based on this uniform, this Cauchy criterion of uniform convergence of this series, जो अभी हमने प्रूफ किया, this is a Cauchy criterion of uniform convergence of series। इसको बेस करके we have a important result in the study of convergence of series, that is known as Weierstrass Mn-test। इसको Weierstrass Mn-test भी बोलते हैं, Weierstrass Mn-test, this is known as Weierstrass Mn-test। okay, so what it states, देखिए कंपैरिजन है यहाँ पर कि आपके पास एक सीरीज है फंक्शंस की और एक दूसरी सीरीज है नंबर्स की। दिस इज अ सीरीज ऑफ फंक्शंस, दिस इज अ सीरीज ऑफ फंक्शंस, and other way you are taking a series of numbers only, and we are taking series of non-negative numbers, नेगेटिव्स को नहीं ले रहे हैं, सीरीज ऑफ नॉन नेगेटिव नंबर्स, ठीक है? तो यहाँ आपके पास नॉन नेगेटिव नंबर्स की सीरीज को हैंडल करना इज मच इजियर देन। तो अगर ये कहता है कि अगर आपके पास इन दोनों सीरीज की जो करस्पॉन्डिंग टर्म्स हैं, एफ एन एक्स के करस्पॉन्डिंग एम एन होगा, इफ इट सेज दैट अगर एफ एन एक्स मॉड ऑफ एफ एन एक्स इज लेस देन और इक्वल टू एम एन, दैट मीन्स एफ एन एक्स बाउंडेड फंक्शन और इसका बाउंड एम एन है। तो और फिर अगर ये सीरीज कन्वर्जेंट है, ये काइंड ऑफ कंपैरिजन टेस्ट की तरह भी वर्क कर रहा है कि अगर आपके पास ये सीक्वेंस ऑफ नंबर्स कन्वर्जेंट है, इफ इट सेज दैट इफ द सीरीज समेशन एम एन इज कन्वर्जेंट, then the series of functions is uniformly convergent। This is much easier, you just have to compare each function with mn, ठीक है? तो you have to see कि अगर आपके पास each function की ये जो corresponding ये जो mn है, तो अगर ये सीरीज कन्वर्जेंट है तो आपकी सीरीज ऑफ फंक्शंस विल बी यूनिफॉर्मली कन्वर्जेंट. नाउ द क्वेश्चन इज कि जब हमें प्रैक्टिकली क्वेश्चंस को कोई एग्जांपल्स को सॉल्व करना होगा तो ये mn's हमें ढूंढने होंगे, ये हमें गिवन नहीं होंगे. और जरूरी नहीं कि हर सीरीज के लिए आपको mn मिलेंगे, ये कंडीशन है कि अगर इस तरीके से सिचुएशन होती है तो फिर सच अ सीरीज, इट इज नॉट अ नेसेसरी एंड सफिशिएंट कंडीशन एज. तो बट वी हैव टू सी, वी विल सी. एंड वन ऑफ द थिंग के जहां आपको ये mn's ढूंढने इसलिए हो सकते हैं, कभी कभी यू यू मे टेक, अगर जब आपको fn का पता है कि fn बाउंडेड है और you might find fn of x का supremum, you might find the supremum of this function, और अगर वो supremum को you might denote with mn. Sometime, most of the time it might work. And then you have to see कि इसके supremum के corresponding, और supremum find करने की कोई भी टेक्निक हम यूज कर सकते हैं. अगर differentiable functions हैं हम डबल डेरिवेटिव टेस्ट से find कर सकते हैं whatsoever, but that's the later part. Let's first look at its proof. So let's look at the proof. So we have to assume that this series of numbers is convergent, and then we have to prove that the series of functions is uniformly convergent. So let us take some epsilon positive number, and it is given that the series of numbers summation fn is convergent. Using the definition of convergence, the Cauchy criterion of convergence of series from numbers, and we are given epsilon greater than 0, so there exists a number, let us denote it by m epsilon, depending on only on upon epsilon greater than 0, such that this is, ये Cauchy criterion से आ जाता है जी series of numbers के ये अगेन जैसे ये पार्शियल सम्स नहीं है, दिस इज सम पीस ऑफ सम m sub n plus 1 plus m sub n plus 2 so on up to m sub m is less than epsilon for every m greater than or equal to n greater than or equal to m epsilon. But most of the time यहाँ पर strict inequality is a much better. ठीक है. Now from the hypothesis we are given, hypothesis में हमें हमारे पास क्या आ जाता है जी, ये चीज आ जाती है. But how this happens, let us see. Let me go back, and I'm going to write this there. I have this thing fn plus 1x plus fn plus 2x plus so on plus fm of x. पहले तो मैं इस पे ट्राइंगल इनइक्वालिटी लगाऊंगा. ट्राइंगल इनइक्वालिटी से इट विल बी लेस देन इक्वल टू एफ एन प्लस 1x plus it will be fn plus 2x plus so on plus it will be mod of fm of x. अब हाइपोथेसिस में क्या किया कि हर एक टर्म जो है दैट इज बाउंडेड बाय कॉरस्पॉन्डिंग टर्म इन द सीरीज ऑफ नंबर्स, तो fn1 plus f of n plus 1 has to be bounded by n plus 1, ठीक है, modulus plus fn plus 2 has to be bounded by m n plus 2 plus so on plus fm has to be bounded by m of sub m. ठीक है. नाउ लेकिन आपके पास जो ये mn's हैं, सिंस आपके पास ये mn's जो हैं दे आर नॉन नेगेटिव, सो दिस ये जो इनइक्वालिटी ये मॉड है तो मॉड सबका इक्वल उसी नंबर के बराबर होगा, तो यू कैन राइट इट टू बी इक्वल टू mn plus 1 plus mn plus 2 plus so on plus m of sub m. So this is the inequality जो हमें मैंने आगे लिखी हुई है जी. This is the exactly thing that we have I have written there, and it comes from the triangle inequality and the fact from that the terms of the each mn is a non-negative, so that mod वहां से हट जाता है, and you are left with this inequality that this is less than or equal to m of n plus 1 plus so on m of n plus 2 plus so on plus m of m. तो इसका मॉड भी ये इसी के बराबर होगा क्योंकि सम ऑफ नॉन नेगेटिव टर्म्स इज अगेन अ नॉन नेगेटिव टर्म. इज इट ओके? एंड दस इट फॉलोज दैट, क्योंकि अब दी राइट हैंड साइड देखिएगा ये जो मैंने लेटेस्ट अब इसको लेट मी रीबॉक्स इट. सो दिस इन इक्वलिटी, look at the right hand side. Right hand side is nothing but it's the same thing there for which you have this mod of m of n plus 1 plus mod of m n plus 1 plus m n plus 2 so on less than epsilon. but ये mod आप ही रिमूव कर सकते हैं क्योंकि नॉन नेगेटिव टर्म्स है, नॉन नेगेटिव टर्म्स का नंबर वो खुद से है. तो दैट मीन्स आपके पास इस सेकंड बॉक्स के अंदर जो राइट हैंड साइड में नंबर्स का सम है तो ये सम लेस देन एप्सिलॉन है. अगर ये सम लेस देन एप्सिलॉन है तो इट फॉलोज दैट द सम मॉड ऑफ एफ एन प्लस 1 x plus fn plus 2x 1 plus fm plus x is less than epsilon for every m greater than n greater than or equal to m epsilon. And this is the requirement of this Cauchy criterion that we just proved this, and hence from that the theorem 1 which I have denoted named as theorem 1, क्योंकि वहां हमने प्रूफ किया कि कोई सीरीज आपके पास यूनिफॉर्मली कन्वर्जेंट है इफ एंड ओनली इफ आपके पास किसी भी एप्सिलॉन के कॉरस्पॉन्डिंग देयर एग्जिस्ट सम नंबर m एप्सिलॉन सच दैट आपके पास ये जो सम्स हैं इन सम्स का मॉड आपके पास लेस देन एप्सिलॉन हो जाए. तो we have this and hence we can say that now from Cauchy criterion or theorem 1 that this series of functions is uniformly convergent. Do you have any problem, any query regarding this? Any questions
नो
on
सर,
this? हाँ जी बोलो.
नो सर, कोई क्वेश्चन नहीं.
Okay, 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 no issue.